In the maintenance hangar behind the terminal, the matte gray metallic narrow-body aircraft stands silently under white lights, with no logo or markings. Check the torque settings on panel 7B. Noted. We'll run the diagnostic sequence now.
These values confirm the stabilization sequence is working, but we should monitor the power fluctuations closely.
But in this clean, quiet, disciplined environment, every small movement of the male engineer, female engineer...
The real question is not how many safety systems an aircraft has, but why the entire aviation system must be built on a safety mindset from beginning to end.
The matte gray metallic narrow-body aircraft cannot declare itself ready, so humans must read every signal, check every detail, and question even what seems normal. At that moment, the contradiction becomes clear. If safety were a feature, it could simply be switched on.
In normal operation, an aircraft is not a simple flying object, but a network linking structure, engines,
The African-American male engineer, aged 25 to 30, does not inspect one part and conclude safety.
The South Asian female engineer, 82 to 25, compares DARE's data with reality, because correct numbers still require...
Workers do not rush to finish, but follow sequence to ensure no step is lost from the system's memory.
A safe flight does not begin when passengers sit down, but long before, in silent inspections behind the terminal.
The matte gray metallic narrow-body aircraft can only leave the ground when all layers of control agree that no signal has been overlooked. In standard operation, safety is not the feeling of reassurance at the end, but the method of thinking before any action is taken.
The male African-American engineer aged 25 to 30 treats every normal reading as something that must be confirmed, not as proof to stop checking.
The female engineer sees the checklist not as a requirement, but as organized memory built from generations of mistakes and corrections. Workers aged 22 to 25 understand that their precision does not only serve the present task, but protects those who will never know their names on future flights. The problem deepens when everything in the hangar appears normal, with no warning sounds, no visible cracks, and no obvious danger signs on the aircraft. That normality creates the most dangerous question, because if everything looks fine, why must the engineers and workers continue strict inspections? If safety were a feature, a system showing no error would be enough. But aviation does not allow full trust in a single signal.
See this irregularity in the component response. It's subtle, but it will slow down the workflow.
I see it. Let's adjust the calibration. The male engineer aged 25 to 30 does not consider that deviation minor, because in aviation, small is defined by consequence, not size. The inertial dampeners are reading below tolerance, but only intermittently. I agree, the aircraft itself looks flawless. There's a contradiction in the data we can't ignore.
The abnormality is not in the aircraft itself, but in how easily humans can be lulled by stable appearances without a guiding safety mindset.
In the maintenance hangar behind the terminal, silence is not simplicity, but the result of countless rules holding chaos outside. Thus, the question becomes real. Does safety in aviation systems reside in equipment, or in how people think before trusting that equipment? The root cause is that an aircraft does not operate as a single function, but as a chain of dependencies, where a small fault in one place can alter conditions elsewhere. Therefore, safety cannot be attached as an accessory, because it must exist in design, maintenance, operation, training, inspection, and even communication. The male engineer aged 25 to 30 understands that a system is truly safe only when it is designed so humans can detect deviations before they become failures.
The African-American female engineer, aged 22 to 25, understands that procedures do not slow work, but prevent memory.
Workers aged 22 to 25 understand that discipline is not rigidity, but protection against human moments of carelessness.
In aviation, safety is a mindset because it forces people to ask, what happens if an assumption fails?
A safety feature reacts when triggered, but a safety mindset acts before danger is even defined. The matte gray metallic narrow-body aircraft does not only need good brakes or warnings, but an environment where no one treats those protections as excuses to relax.
The male engineer aged 25 to 30 reviews the final report again, because a safety mindset treats a correct answer as the start of another confirmation.
If safety is compared as a feature versus a mindset, the first difference lies in when it appears.
A feature appears when a situation demands reaction, but a mindset appears before touching the aircraft, already thinking about possible deviation.
The second difference lies in scope, because a feature protects within its design limits, while a safety mindset covers data reading, questioning, and justified doubt.
The third difference lies in responsibility, because a feature belongs to equipment, while a mindset belongs to engineers, workers, and the entire system.
In the maintenance hangar behind the terminal, no one claims a single component ensures safety, because safety is built from layered vigilance.
When the East Asian male engineer aged 25 to 30 calls for another check, it is not distrust, but a culture where evidence replaces assumption. When the engineer questions a small value, it is not hesitation, but the system protecting itself from premature confidence.
When workers aged 22 to 25 slow a task to follow procedure, it is not inefficiency, but the understanding that speed never overrides safety. Check the alignment on the tertiary coupling. The schematic suggests a tighter tolerance here.
Rerunning the diagnostic. It is within the safety margin.
An aircraft with advanced features is not enough if operated with a careless mindset, but a strong safety mindset forces technology to be verified correctly.
The conclusion is clear. Safety is not a feature in aviation systems, because no button, sensor, or device can replace disciplined thinking. Safety is a mindset, because it begins before design, continues through maintenance, exists in operation, and remains after landing. The South Asian male engineer aged 25 to 30, the Hispanic female engineer aged 22 to 25, and the African American worst. The matte gray metallic narrow-body aircraft stands still in the maintenance hangar, but around it exists a Without that mindset, safety features become isolated protections, strong individually, but weak as a system.
With that mindset, every checklist, every action, every glance, and every recheck becomes part of a larger protective system.
That is why aviation does not teach people to assume everything is correct, but to build systems where errors cannot travel far. Under the white lights of a clean, quiet, disciplined hangar, safety does not appear as a device, but as a repeated habit of thinking. Wait. And when the aircraft leaves the hangar to return to the sky, what lifts it is not only engines or wings,